Welcome to Solving Trigonometric Equations. For this video, be sure that you have handy your unit circle and your trig reference sheet, as we will be using both of those a lot. Let's start with the warm-up. Go ahead and try this and then hit play again when you think you got the answer. Here is the solution. Our solution for cosine x equals negative root 3 over 2 is that x equals 5 pi over 6 and 7 pi over 6. Note that I'm not writing 5 pi over 6 plus 2 pi k and 7 pi over 6 plus 2 pi k where k is an integer, because we're asked that x lies in the interval from 0 to 2 pi. Now, if we added 2 pi k, that would mean starting at 5 pi over 6 and going around multiple times, or going backwards if k was a negative number. But if we did that, then our angle would be either too large, it'd be past 2 pi because we'd be passing 2 pi, or it'd be too small, we'd be going back around and subtracting an entire 2 pi, it'd be less than 0. When we're asked, and same idea for 7 pi over 6, that is why there's only 2 solutions here and not an infinite amount of solutions like we've been previously used to answering our questions. When we are given an interval for our answer, we do have to make sure that the answers that we give do lie in that interval. The interval that we'll see most often is 0 inclusive to 2 pi non-inclusive, and that is just one full revolution around the unit circle, but not including 2 pi at the very end. In this video, we will see trig equations that are a little bit more complex than ones like this, that we're straight up just have x or theta inside our trig function. We will see things like the cosine of 2x equals negative root 3 over 2, maybe the cosine of x plus pi equals this, things that are a little bit more complicated. So again, make sure you have your unit circle and your trig reference sheet, as we will be using both of those to solve more complex trig equations. Let's get started. For this example, we want to solve for theta in between 0 and including 0 and 2 pi not including 2 pi. So again, only values that are on our unit circle and not going past the 2 pi. We see in number 1 that we have the cosine of 2 theta equals negative root 3 over 2. In our warm-up, we saw that the answer to the cosine of theta, or the cosine of x, equals negative root 3 over 2 on our unit circle was at 5 pi over 6 and 7 pi over 6. And so we know that the things that we want on the inside here, what 2 theta equals, is 5 pi over 6 and 7 pi over 6. Because if we plug that in for 2 theta, we would have a true statement here. So let's set 2 theta equal to both of those. So I'll start with 2 theta equals 5 pi over 6. And I am going to add plus 2k pi, because in this case, we don't know that when we eventually solve for theta, that we might have another answer that's still on our unit circle. This is not just theta or just x in here anymore, it's 2 times theta. So we do have potential other answers that still lie in our one revolution on our unit circle in between 0 and 2 pi. We will have another equation down here, but I'll start with solving this one. Let's divide everything by 2 to solve for theta. That's our ultimate goal. Now, instead of writing divided by 2, I'm actually going to write multiplied by 1/2, because we have some fractions here and I don't want it to get too messy. Now, on the left-hand side, we'll obviously be left with theta. Then when we multiply 5 pi over 6 times 1/2, we'll have 5 pi over 12. And then when we multiply the 2k pi by 1/2, we'll have just a 1k pi. We know that k is an integer, and if k was 0, we would just have 5 pi over 12 plus 0. So we just have 5 pi over 12. And 5 pi over 12 is on our unit circle in between 0 and 2 pi. So I'm going to kind of make a little, like a thought bubble over here, and let's let k be some values and see what theta would be in that case. And we want to see if that theta fits in this interval here. Well, if k was 0, we have our one answer, which is 5 pi over 12, and that works. It's in between 0 and 2 pi. It's literally 5/12 of a pi, so it's not even one whole pi. Well, what if k was an integer close to 0? Let's say k was negative 1. If k was negative 1, we'd have 5 pi over 12 minus a whole pi. So if we took 5/12 of a pi and subtracted a whole pi, 12/12 of a pi, we'd have negative 7 pi over 12. Is negative 7 pi over 12 in between 0 and 2 pi? It is not. So this is not an answer that can work. Let's try k equals 1 and see what happens there. If k was 1, 5 pi over 12 plus 1 whole pi, we'd have 5 pi over 12 plus 12 pi over 12, which would give us, let's see, 17 pi over 12. Is 17 pi over 12 in between 0 and 2 pi? Well, 2 pi is 24 pi over 12. This is definitely in between 0 and 2 pi. So this is actually another answer that works. And that's why we still had to add that 2k pi here, because we had kind of a more challenging trig equation, and our theta, we could potentially squeeze in another answer here. If k was 2, we'd clearly be too big. If k was 2, we'd be adding on 2 whole pi here. And clearly this is something greater than 0, and if we're adding on 2 pi, we're going to be greater than 2 pi. So I don't even have to do the algebra here. I already know that's not an answer. But the interesting thing is that this is giving us 2 solutions. So I'll list the 2 solutions for theta from this first equation are 5 pi over 12 and 17 pi over 12 because of adding on a k pi. The next equation that we need to write, remember we started off with this inside here equaling 5 pi over 6. The other possibility for that 2 theta, as we saw, where cosine equals negative root 3 over 2, was at 7 pi over 6. So we're going to do this again with 7 pi over 6. All right, so we're going to have our other potential solution here is 2 theta equals 7 pi over 6 plus 2k pi. When we multiply both sides by 1/2, we'll again get our theta by itself, which is our goal. So we'll have theta equals 7 pi over 12 plus k pi. Well, again, we have multiple solutions here. Clearly 7 pi over 12 is one solution. It lies in between 0 and 2 pi. And so when k was 0, we just got 7 pi over 12, and that's one of our solutions. What about if k was negative 1, and we subtracted a whole pi? We'd have 7 pi over 12, which again is not a whole pi. It's only 7/12 of a pi. So if we subtracted a whole pi, we'd be less than 0. So this is not going to work. What if k was 1? If k was 1, we'd be adding 7 pi over 12 plus a whole pi. 7 pi over 12 plus 12 pi over 12. Well, 7 plus 12 is 19, so we would have 19 pi 12ths. Adding 2 pi would be too big. Now 19 pi over 12 is in between 0 and 2 pi, so that's another potential solution. So this one gives us also 2 solutions here. So our final 4 solutions to this are 5 pi over 12, 17 pi over 12, 7 pi over 12, and 19 pi over 12. So these are our 4 solutions. I'm going to write them in order from least to greatest. So we'll start with 5 pi over 12, then 7 pi over 12, then 17 pi over 12, and lastly 19 pi over 12. And those are our 4 solutions for theta that lie on the interval between 0 and 2 pi. Our next equation looks very similar. We have the sine of theta over 3 equals root 2 over 2. Well, if we had just the sine of theta equals root 2 over 2, we just want to look at our unit circle and see where the sine is root 2 over 2. Well, we know that the root 2 over 2's go with the pi over 4 family, and sine is positive in quadrants 1 and 2. So what's inside here needs to equal pi over 4 and 3 pi over 4, since that's where the sine is root 2 over 2. So we're going to have 2 equations that we'll need to solve. Again, our first equation will be that what's inside here, theta over 3, needs to equal pi over 4 plus all the way around 2k pi. And then our other equation is theta over 3 equals 3 pi over 4 plus 2k pi. Again, since the period of both sine and cosine is 2 pi, we have to add on that 2k pi or 2 pi k, however you want to write it. Here we need to solve now for theta because this is just answering the question, what is theta over 3? We want to solve for theta. Well, in order to get theta in both cases, we need to multiply both sides by 3. When we do that, we'll have theta equals 3 pi over 4 plus 6k pi. Then down here, when we multiply both sides by 3 to solve for theta, we'll have theta equals 9 pi over 4 plus 6k pi. Now let's explore some values of k. K is an integer, recall. So if k is 0, which is the easiest to plug in, our answer for theta would just be 3 pi over 4. And 3 pi over 4 is clearly in between 0 and 2 pi. Now, what if k was -1, if we talk through this one a little bit? If k was -1, we'd have 3 pi over 4 minus 6 pi. That is way too small. It's clearly going to be a negative number. This is not even a whole pi, and we're subtracting 6 pi's. That's less than 0. What about if k is 1? Since we can't go more negative, what about if k is 1? Well, if k is 1, we'd have 3 pi over 4, and we're adding 6 whole pi's. That's clearly bigger than 2 pi, so that's not even going to work. I don't even need to do the math there. We can just do number sense. So our only solution here to this equation is 3 pi over 4. So that ends up being our only solution to that equation. What about this bottom equation down here? Well, if we take a look at what values k could be, again, if k is 0, our theta would simply be 9 pi over 4. And 9 pi over 4, let's think about it. Is 9 pi over 4 in between 0 and 2 pi? No. 9 pi over 4 is too big. It's greater than 2 pi. 8 pi over 4 would be 2 pi, and we can't even equal 2 pi. We have to be less than it. So this actually doesn't work. It's too big. What about if k was -1? We can't go bigger. So what if k was -1? Well, we'd have 9 pi over 4, which is a little bit bigger than 2 pi, and then we'd be subtracting 6 pi if k was -1. That's way too small. We have something that's just a little bit over 2 pi, and we're subtracting 6 pi. 2 pi's minus 6 pi's, negative. So that's not going to work either. It's less than 0. So this equation actually doesn't provide us any solutions. I'm actually not going to put a no solution symbol there because this problem has a solution. It's 3 pi over 4. Just this particular equation from it doesn't. So I'll just put an X, whatever. So the only solution here is that theta equals 3 pi over 4. And that's the only one that works for the sine of theta over 3 equals root 2 over 2. What I'm actually going to do here is show you that it does work. So I'm going to check our answer here. So we're going to check our answer that theta can equal 3 pi over 4. All right, let's check it. So we'll have the sine of 3 pi over 4 and then divided by 3. So I'll put times 1/3. So I just plugged in theta as 3 pi over 4. And dividing by 3 means multiplying by 1/3. We want to make sure that that equals root 2 over 2, so I'll put a question mark here. So this is really, these 3's cancel, so this is the sine of pi over 4 equals root 2 over 2. Is that true? Yeah, the sine of pi over 4 is in fact root 2 over 2. Now, while other thetas could technically make this true, like what we found 9 pi over 4, if we plugged in 9 pi over 4 for theta, it would make this a true statement. However, the reason that 9 pi over 4 was not a viable solution is that it doesn't lie in between the interval between 0 and 2 pi. So our only solution here was 3 pi over 4 because not only did it make the statement true, it fell in the indicated interval. Here we want to solve cosine of x plus 5 pi over 6 equals 0. So let's see, where is the cosine 0? Then we'll set what's inside here equal to that, since that will make it true. Well, the cosine is the x value, as we know, and that means the cosine is 0 at pi over 2, and the cosine is 0 down here at 3 pi over 2. So this is an interesting one. Normally, what we would do is we would list both of these and add 2k pi. However, if we look and see, because of the unique placement of these angles here where the cosine 0, if we start at pi over 2, we just have to add a pi to get to the next spot where cosine 0. So this one's unique in that we'll only have to set up one equation for this one. So we want what's inside here, this whole thing, we want it to equal pi over 2 plus k pi. Since adding a pi will get us here, adding another pi will get us here, subtracting a pi will get us back to where we want. So we will set x plus 5 pi over 6 equal to pi over 2 plus k pi. Again, a unique situation, the cosine is 0. We normally add 2k pi for cosine and sine since that's their period, but unique situation here, we can just have 1. Now in these problems we're solving for x, it's the exact same as solving for theta. We want to get x by itself. So getting x by itself means subtracting 5 pi over 6 from both sides. Now when we do this, we cannot subtract it from the k pi, since k pi is not a common term to these guys right here. So when we subtract this, we'll have x equals, and then we have 3 pi over 6 minus 5 pi over 6. So 3 minus 5 is negative 2 pi over 6, which is negative pi over 3, plus k pi. Now, let's see what values of k we can have since now x is by itself. Let's see what values of k will make sense here. K is an integer, so the simplest integer would just be 0. Well, if k was 0, we'd have negative pi over 3 for x, and that doesn't work. It's not in between 0 and 2 pi, it's less than 0. So let's plug in another value for k. We can't go more negative, so let's plug in a positive 1 for k. If k is positive 1, we'd have negative pi over 3 plus pi. So we'd have negative pi over 3 plus 3 pi over 3. So that would give us positive 2 pi thirds. That works. That's in between 0 and 2 pi. Then next, let's see if we can go even bigger. Let's plug in 2 for k and see what happens. We'll just keep going until it's too big and it's past 2 pi. So if we plug in 2, we'd have negative pi over 3 plus 2 pi, which is negative pi over 3 plus 6 pi over 3. So that would give us 5 pi over 3. And 5 pi over 3 is less than 2 pi. 6 pi over 3 would be 2 pi, so that works. Now we're very close to 2 pi, that if we added another pi, if k was 3, we'd be too big. So clearly if k was 3, we'd be too big. So we actually have two solutions here for x. Our two solutions are 2 pi over 3 and 5 pi over 3. In number 4, we have the sine of 4x equals negative 2 root 3 over 3. Now this is not a sine value that we have seen on our unit circle. The sine values that we see and are familiar with are 0, 1/2, root 2 over 2, root 3 over 2, 1, and then there are negatives down below. Well, that doesn't mean that this cannot be a value of sine. After all, what about, pi over 12? Some random spots. There's an infinite amount of points on the unit circle, an infinite amount of angles. However, we have to make sure that this could be a valid sine value, basically. Now, if we look and see, all sine values, the smallest they can be is negative 1, and the greatest they can be is 1. The range of sine is negative 1 to 1 inclusive. So if this value is in between there, it could potentially work. Let's see what value this is. Plugging negative 2 root 3 over 3 into our calculator gives us approximately negative 1.15. So we do not have any angles on our unit circle that can output that kind of sine value. We can clearly see that the greatest sine value we can have is 1. We can't go past that on the unit circle, and the smallest we can have is negative 1. So there is no x angle here, angle called x, that even 4 times it will output a sine value that's less than negative 1. Now, another way that you can do this if you did not see that right away is you can take the arc sine of both sides. So if we take the arc sine of the sine of 4x, and then we take the arc sine of this value here, negative 2 root 3 over 3. We can do that because we're doing the same thing to both sides. And sine and arcsine do undo each other. They are inverse operations of one another. So the left-hand side of this simply becomes 4x. This is an alternate way to solve. And then in your calculator, in order to get arcsine, this is alternately known as, and I mentioned this in the previous video, the sine inverse, or sine negative 1, of this value right here. Now on your calculator, there is a sine button, and right above it, it says sine inverse. If you hit the second key and then the sine key, you will get the sine inverse. When you plug this in, it will give you an error. And that is because we cannot plug in values into arcsine or sine inverse that are outside of the range of the sine function, that are less than negative 1 or greater than 1. So this problem does not have a solution because there is no possible way that a sine value on our unit circle can be less than negative 1. In number 5, we have the secant squared of x equals 4. Well, we can rewrite this as the secant of x quantity squared equals 4. These two are equivalent ways of writing it. We simply write it this way. It's just the way math is notated for trigonometry. We do not write it as the secant of x squared. X is not being squared. The secant of x is being squared. So that's the difference. Now I write it this way because visually I think this is just more appealing. Then we can clearly see how to solve for secant. When we take the square root of both sides, we will have the secant of x equals plus or minus 2. The secant is the reciprocal of cosine, so we can think about this as the cosine of x equals plus or minus 1/2. That's easier probably for our brains to look at the unit circle, knowing that when the secant is 2, the cosine's 1/2, and same with negative 2 when the cosine is negative 1/2. Now, in this case, there's not really much else to solve for. We can simply look at our unit circle to see where the cosine is positive or negative 1/2. Well, our cosine is 1/2 at pi over 3 and 5 pi over 3. Our cosine is negative 1/2 at 2 pi over 3 and 4 pi over 3. So basically at the pi over 3 family. We can write this as just listing those 4 values. That's probably the easiest way. We don't need to add any k pi's or 2k pi's to anything because we are simply solving for x in between 0 and 2 pi. So again, our 4 answers for x are going to be the pi over 3 family. So pi over 3, 2 pi over 3, 4 pi over 3, and lastly, 5 pi over 3. The biggest thing here is that when you take the square root in an equation, when solving an equation, you do need to make sure you put the plus or minus in front of it because otherwise you would be missing half of the answers. Number 6 is quite a challenge. We look and see that we have the cosine of 2x, that's a double angle, equals 3 cosine of x minus 2. So we are dealing with a cosine of a 2x in the same problem that we're dealing with a cosine of an x. We cannot combine these because this is a different term than this. They're not like terms. So instead we can see that we do have a double angle. If you look on your Trig cheat sheet or back in your notes, we learned about double angles and we see that the cosine of double an angle all the way down here has 3 different ways of writing it. Because we're dealing with a problem that has another cosine in it, I don't want to introduce replacing cosine of 2x or 2 theta with something that has another trig function in it, meaning sine. So I'm actually going to choose this one right here, and I'm going to replace the cosine of 2x with 2 cosine squared of x minus 1. Again, using the double angle formula. So we have replaced cosine of 2x with what it equals because this is a double angle formula. The right-hand side is not changing at all. Now, what we have is we have a cosine squared, we have a cosine, and we have some constants. Let's get everything to one side because we have a quadratic. So we are going to add the 3 cosine of x to both sides, or rather, actually we're going to subtract 3 cosine of x from both sides, and we're going to add 2 to both sides. getting everything to the left-hand side, because we want to set this to 0 because that is how we solve a quadratic. So we'll have minus 3 cosine x. Then when we add 2 here, it'll get rid of this. When we add 2 to this, since they're like terms, we'll have a plus 1 equals 0. Now we can clearly see that we have a quadratic. What I'm actually going to do is use a substitution. So I'm going to just use a variable. We can use any variable we want. I will use the variable u. So we're going to let u equal the cosine of x. So that means this term right here is 2 times u squared. So we'll have 2u squared. Then we'll have minus 3u plus 1 equals 0. You can probably see why we did this. It makes our quadratic look a lot simpler. Then let's see if this is factorable. A times c, 2 times 1 is 2. Are there two numbers that multiply to 2 that add to negative 3? Yes, those numbers are negative 2 and negative 1, so we'll rewrite this as follows. Replacing that middle term with minus 2u and minus 1u, so we're factoring by grouping here. So our first two terms have a GCF of 2u, we'll be left with u minus 1. And then our second two terms have a GCF of minus 1, since again we want to be left with u minus 1. So to factor, we'll have 2u minus 1 and u minus 1. So solving for u, we'll set each factor to 0, so we'll have 2u minus 1 equals 0, and we'll have u minus 1 equals 0, so we'll have u equals 1/2, and then we'll have u equals 1. Now what we're going to do is actually back substitute. We see here that we let u equal the cosine of x to make factoring simpler. Did we have to do that? We didn't, but it makes the factoring a lot simpler. Now I'm going to back substitute and put back in the cosine of x for u. We're just going to go backwards. So we'll have the cosine of x equals 1/2, and we'll have the cosine of x equals 1. These are fairly simple to solve. We just need to look on our unit circle to see where is the cosine 1/2. We kind of looked at that in the previous example. The cosine is 1/2 at pi over 3 and at 5 pi over 3. So those are our two solutions here. Then our second equation, where is the cosine of x equal to 1? The cosine is equal to 1 only at one spot over here. Now this spot right here is 0 and 2 pi and 4 pi and 6 pi, but it's 0 and 2 pi right here. Well, we want our x values to lie within the interval equaling 0 and up to but not including 2 pi. So the way that we're going to answer this for x is simply that x is 0 here, because the cosine of 0 is 1. Writing these three solutions in order, we will have that x equals 0, pi over 3, and 5 pi over 3. That one was a little bit crazier because it did involve some factoring and use of a substitution. We will see another example like that shortly. In number 7, we have the sine of x equals the cosine of x. We again want to solve for any x values in between and including 0 and 2 pi, not including 2 pi. All right, so this is one where I don't really have any special tricks up my sleeve. Let's just look at the unit circle and see where does the sine equal the cosine. It's really as simple as that. I mean, I'm sure there's ways that you can do this that are more savvy mathematically, but for ones like this, let's literally see where they equal each other. We know that at like the pi over 6 and pi over 3 families, the cosine and the sine don't ever equal one another. But if you look at the pi over 4 families, that's where we have that potential. Well, we can clearly see that at pi over 4, the sine and the cosine equal each other. So it looks like pi over 4 is one answer for x. Awesome. Where else do the sine and the cosine equal each other? Not at this pi over 4. They're opposites. But down here at 5 pi over 4, they're equal once again. At 7 pi over 4, they're opposites again. So our other answer is 5 pi over 4. Now, there's no other spot on the unit circle where the x and y coordinates ever have the potential to be the same. So it looks like those are our only solutions in between 0 and 2 pi. I saved number 8 as our last one because it's a good one. We have the secant squared of x equals the tangent of x plus 3. Whoa. We have two different trig identities here, or trig functions rather, but we do see that we have something squared. Now, when we have something squared, a lot of times you should think Pythagorean identities. Remember, the main Pythagorean identity is sine squared plus cosine squared equals 1. And the other ones are on your trig reference sheet, and they should also be in your notes. So we can see that we have the Pythagorean identities right here, and that secant squared can be written in terms of tangent. Awesome. So the secant squared of theta, or of x, is the tangent squared of theta plus 1. So let's replace secant squared of theta with what it equals. It equals the tangent squared of x plus 1. And then our right-hand side, again, still in terms of tangent. So just like in our example number 6, where we had a cosine squared and a cosine term, here we have a tangent squared term and a tangent term, we have a quadratic. Let's get it set equal to 0 because that is how you solve a quadratic. Let's keep our squared term positive, so we'll keep the tangent squared of x on the left-hand side. Then I'm going to subtract the tangent of x from both sides. Then I'm going to subtract 3 from both sides to get this side equal to 0. So when we subtract 3 from 1, we'll have minus 2. So we have our quadratic. It's equal to 0. We have 3 terms in our quadratic. And what we're going to do now to make this a little bit simpler is we're going to use substitution. So I'm going to let u equal the tangent of x. So we'll let u equal the tangent of x. I'm using u because in calculus, we have something special called a u substitution that you'll see next year. And so just using that variable is letting us get comfortable with it. You can use any variable, probably except x. That would be a good idea. All right, so we let u equal the tangent of x. That means we can rewrite our quadratic as u squared minus u minus 2 equals 0. This is a quadratic that's a little bit simpler to factor because our a value is 1. In number 6, our a value was not 1, so we had to do factoring by grouping. Here, we simply want to see if there's two numbers that multiply to -2 that add to -1, and there are, and we can go right into the two parentheses here. Those numbers are -2 and a +1. Solving for u, we'll set each factor to 0, and we'll get that u can be 2 or u can be -1. Now what we're going to do is back substitute. Remember, back substituting just means going back from what you originally substituted. So we're going to replace u back with what it equals, which is the tangent of x. So the tangent of x equals 2, and we'll have the tangent of x equals -1. Now I do want to be sure that your calculator is in radian mode. We have been dealing with radians for this entire video. Whenever you're dealing with radians, you want to make sure your calculator is in radian mode. And so in your calculator, you hit the mode button, and then go down, you'll see it says radians and degrees. You want to make sure that you're in radian mode instead of degree mode. I'm saying this because we want to solve for the tangent of x equals 2 and the tangent of x equals -1. Well, the tangent of x equals 2. Do we know on our unit circle if the tangent is ever 2? It's not. And that's because we know that the tangent here is 0. Here, the tangent is going to be √3/3. Here it's 1. Here it's √3. And then here it's undefined. And it repeats that pattern. 2 is not a common tangent that we see on our unit circle. It's not a common tangent value. However, that doesn't mean that it can't exist. Because again, there are infinite amount of points on the unit circle. These are just the main ones. Well, in order to solve this, we're going to take the arctan of both sides. So we'll take the arctan of the tangent of x, and then on our right-hand side, we'll take the arctan of 2. So we're taking the arctangent of both sides to solve, because we can't solve this in a simple way by just looking at the unit circle. Well, the arctangent of the tangent of something is just that something. And then on the right-hand side, so we'll have x equals the arctan of 2, and then the period of tangent is pi, so we can add k pi. So again, we're not adding 2k pi because it's not sine or cosine. It's k pi because the period of tangent, it like repeats every pi instead of repeating every 2 pi. All right, so we're adding k pi. Now, this one's interesting. We do need to make sure we go on our calculator and see kind of what these solutions can be. Well, if k is 0, again, let's take a look here. If k is 0, then our output x is simply the arctangent of 2. Well, what is the arctangent of 2? So in our calculator, we're going to hit the second key, the blue key, and then our tangent button. That'll give us inverse tangent. So it's a tangent and a little -1. That gives us, if you're in radian mode, which you should be, it gives us 1.107. Now, is 1.107 a radian measure in between 0 and 2 pi? Well, if we think about what 2 pi is as a decimal, it's twice pi. Pi is 3.14 approximately. Twice that is 6.28. This is clearly in between. So that works. Now, what if we added a whole nother pi to this? What if k was 1? If k is 1, then we're taking the arctangent plus pi. So in our calculator, I'm just going to add pi to my answer. When I add pi to my answer, I'm going to get approximately 4.249. That is again in between 0 and 2 pi. Now, if I added another one, I'd be too big. I'd be past 2 pi. If we started here, and if k was -1, so if we started at the arctangent of 2 and subtracted pi, if we started here and subtracted pi, we'd be too small. Pi is 3.14. If we took this value and subtracted 3.14, we'd be at a negative value below 0. So we can't go there either. So we have two answers here. Those answers are the arctan of 2, which is approximately 1.107. And then we also have that x could be the arctan of 2 plus pi, which is approximately, as we saw, 4.249. So far our answers are I'll put an approximate, 1.107 and 4.24. Again, those are radian values. Not all radian values need a pi in them. Okay, that was a lot, but we got our values for the equation tangent of x equals 2. How about the tangent of x equals -1? Well, luckily for us, we don't have to go through that whole process again because -1 is a common tangent value. Where is the tangent -1? Well, the tangent is -1 when the x and y coordinates are opposite from each other. So when we divide y by x, we'll get -1. So at 3 pi over 4, our tangent is -1, and also at 7 pi over 4. Those are the two solutions on the unit circle where the tangent of x equals -1. So for in this case, x equals 3 pi over 4 and 7 pi over 4. So our four solutions are these two decimal approximations that we got, as well as 3 pi over 4 and 7 pi over 4. Those are our four values for x. Now, I agree that that problem was much more difficult than the majority of the others we did in this video. If that one was really the only one that was confusing to you with the whole process we had to go through, then you should be fine. However, if any of the first 7 were a little bit confusing, I'd recommend making sure that you know how to do each one of them, going back through them. Again, if 8 is the only one that challenged you a little bit, then you're probably okay. Nice job getting through all of this. Hopefully you feel much better at kind of applying a lot of these things we learned about trig in order to solve some pretty complicated trigonometric equations.